All right, this is a video lesson for Unit 5, Lesson 3. What makes this lesson special is that we are going to know sigma. That doesn't sound like anything too special, but sigma is not always going to be known in the problems that we do. It's actually almost a little bit unrealistic to know it, but this is a really easy transition lesson for us. So that's the reason we're definitely going to do it. But sigma known is the big quality that makes this problem special. So these are going to be mean problems with sigma known. Our next lesson will be about mean problems with sigma unknown, and then our final lesson will be about proportion problems. So these steps right here should look really familiar from Lesson 2's notes. It's all the same stuff, but now we're actually going to apply it all in one problem and see how we chain it all together. So step 1, well, before we even do that, let's look at what the problem is. People have died in boat accidents because of an obsolete estimate of the mean weight of men being used. This is a problem we did in class and talked about. We're going to test this out. We obtain these results. N is 40, so we have 40 people in our sample. Of that sample, the average weight was 172.55. We know that sigma equals 26. That makes this a sigma known problem, which means a different test statistic than when sigma is unknown. We're going to use these results to test this claim. The claim is that men have a mean weight greater than 166.3. Now, a lot of times they're going to tell you in the problem alpha, and that's what this 0.05 significance level means. But let's go through our steps. So step 1, we need to determine the mean and the standard deviation, or sorry, the null and the alternative hypothesis. So our null hypothesis and our alternative hypothesis. Well, we got to ask ourselves, is this a mean problem or is this a proportion problem? Well, we see a couple of times, we see an x bar, which is a mean, and we see the word mean right here. This is definitely a mean problem. So that means that both hypotheses are going to use mu. They always use the same symbol as each other. The number suggested in the claim is right here. The number suggested in the claim is 166.3. So we're going to put that here and here. Whatever number is suggested in the claim always goes here. The null is always in equals, so we're going to put equals. And now the word we're looking for is some word that indicates whether this is a less than or a greater than problem. And right there it is. Greater than 166.3. So this is a greater than alternative hypothesis. And there we go. We've got our hypotheses. Now we move into our alpha. Well, they told us alpha in this problem. They told it to us right here. They said 0.05 significance level. Significance level means alpha. So our alpha is going to be 0.05. So I got my hypotheses, I got my alpha. Because this is a sigma known mean problem, we're going to use this test statistic. There's 3 to choose from, as you saw in Lesson 2, and we know we're going to use this one. Okay, and we should be familiar with these letters. N is what the sample size, x bar the sample mean, not the population mean, which comes from the hypotheses, but the sample mean. Mu is the population mean, which comes from the hypotheses, and sigma is that known standard deviation that we have. In the next lesson, it's going to be unknown. So we're going to be calculating this test statistic. Well, we need x bar. If I go back up to this problem, my x bar was given to me as 172.55. The mean is going to come from my hypotheses, so I don't even have to look back at the original problem. I can just look at my hypotheses. The mean, the mu, is 166.3. We assume the mu is true from the null. So 166.3. Yep, 166.3. The standard deviation is known in this problem. It was stated to be 26. Divided by the square root of n, which is a sample size in this problem of 40. N equals 40. So if this test statistic looks familiar to you, it should. This is actually the central limit theorem. What we're going to do in this problem is we're going to find the probability of getting this sample back, this sample mean back, if this 166.3 from the null hypothesis were true. So we're going to see if that 166.3 is true, what's the chances we get this? If the chances are really low, we're going to be able to conclude that it doesn't make sense to say this is true, and we'll reject that. If the chances are not low, then we'll say, I don't think we can reject it. We don't know for sure, but we can't reject it. And that's called a fail to reject. So that starts to help you understand where this p-value comes from and what it means. Okay? Well, let's type this into our calculator. I'm going to put in parentheses 172.55 minus 166.3 divided by, and then I'm going to put in parentheses 26 divided by the square root of 40, and I get an answer back of 1.52. So z equals 1.52. So we've got our test statistic. Now we move on to our p-val. So the p-val is going to say, is this positive 1.52? What's the probability of that? And we're going to find that going to the right. The reason we're going to go to the right is because the null hypothesis was greater than. So we're going to see what are the chances of getting 1.52 or bigger as the z-score. If those chances are low, then it's probably not true what we assumed at the beginning. So I'm going to draw a picture. I'm going to go to the right. So it's going to be normal. And again, I went to the right because it was a greater than in the alternative hypothesis. If it was a less than, I would have gone to the left. So normal CDF, 1.52 to the right 10, 0, 1. And let's see what we get. I go to my calculator, normal CDF, 1.52, 10, oops, 0, 1. I get an answer of 0.064. And that's your p-val. That's your p-value. Now, we have to determine whether or not we should reject or fail to reject. It's all about this. Is the p-value less than or equal to alpha? Well, our p-value was 0.064. And we're asking, is that less than or equal to our alpha, which if you remember from the beginning of the problem, we set to be 0.05. The 0.05 significance level is what we call that. So is this true? Well, the answer is no. Not true. So we fail to reject, and we can write that as FTR. We fail to reject the null hypothesis. We cannot conclude that the null hypothesis was incorrect. Okay? So if we go back to like the understanding of this problem, we're saying we don't have enough evidence to show that if this is really true, we couldn't get back this. There's a 6% chance that even if the real mean is 166, that we get back a sample mean of 172 based on our sample size. There's not enough evidence to show that this isn't true. Okay? If you don't understand that, just be procedural about it. Just state, we fail to reject the null. Now, in the non-technical conclusion, we're going to kind of follow that script that we had used before. I follow it a little loosely because I really understand it. But if you need to, go back to the L2 script, okay, and state it that way. When we fail to reject, we're going to state our answer like this. There is not enough evidence at the 0.05 significance level to show that, so you're always going to say something along those lines. You would say there is enough evidence if we were rejecting, but when we're failing to reject, there's not enough evidence Okay, there's not enough evidence at the 0.05 significance level to show, and then we're just going to put the HA, the alternative hypothesis, into words. The alternative hypothesis right here had said that the mean weight of men is now greater than 166.3. So that's what we're going to say, that the mean weight of men is greater than 166.3. So what we've done in this process, if we reject, is we get to say the alternative is true. If we fail to reject, then we don't have enough evidence to say the alternative is true. We never confirm or deny the null. We always we say we reject it or fail to reject it, and then we talk about the alternative when we put it into words. So now what we're going to do is we're going to come down here and we're going to do a whole problem all at once, which sounds bad, but I actually think this is going to be the easiest thing for you now that when you see everything done at once. Okay, so this is what a real test problem would look like. We're going to start off by writing out our hypotheses. That's step one. So our null and our alternative hypotheses. Okay, well, a jewelry designer claims that women have a wrist breadth, so this is the claim, equal to 5 centimeters. Okay, so the claim is that women have wrist breadths with a mean equal to 5. So the word mean tells me this is a mu problem. So I'm going to put mu in both the null and the alternative. The number being suggested is 5. So I'm going to put that here and here. And all they've said is equal to. If they don't say greater than or less than, all we can do is treat it as a not equal to problem. Remember, the alternative always has to be an inequality symbol. So I'm going to use not equal to for that. Okay? So step one was get your hypotheses. Step two is to set your significance level. Let's see if they tell it to us. They say use a 0.05 significance level. So that means alpha is going to equal 0.05. So there we go. I've got my hypotheses, I've got my significance level. Now I need to figure out which test statistic I'm using. This is obviously less than 3, so we're going to use the less than 3 test statistic, but let's see why. The reason I'm going to do that is because they tell me the population standard deviation, that means sigma, is 0.33. That means I know sigma. If I know sigma, I'm going to use this test statistic that we learned today. X bar minus mu divided by sigma divided by root n. And now we're going to start filling it in. The standard, or the sample mean. So we're talking in this sentence, a simple random sample. We're talking about the statistics now. We're talking about what evidence has been collected. So the evidence that's been collected is a mean of 5.07. Well, if that's a sample mean, that's an X bar. So this is our X bar right here. So X bar is going to be 5.07. Mu is always going to come from your hypotheses. So that's 5. Standard deviation was stated in the problem. Remember right here, 0.33 is the population standard deviation. And our N, our sample size here, there's 40 women in the sample. So N is 40. And that's going to be our Z. So let's calculate it in the calculator, and then we'll move on to the p-val and everything else. So our Z is going to be parentheses 5.07 minus 5, close parentheses, divided by parentheses 0.33 divided by square root of 40, close parentheses. I get an answer of 1.34. That's my Z-score, or my test statistic. So we're making some good progress. Now, after we get our test statistic, the next step, according to this whole list up here that we talked about, right here, the next step after, so I got this, I did this, I did this, I did this. The next step, the next step is this. Step 4, determine the p-val. So we got to draw a picture and look at that z of 1.34. So z being 1.34, are we going to the right or the left? Well, it's a not equal to problem. And in not equal to problems, you might need to look back at your L2 notes. In not equal to problems, if it's positive, we go to the right, and if it's negative, we go to the left. Well, this is a positive number, so I'm going to go to the right. And then you've got to multiply your answer by 2 for not equal to problems. So our p-val here is going to be our normal CDF. We're going to go to the right, so 1.34, comma 10, comma 0, comma 1, and then we're going to take that answer and we're going to multiply it by 2. We can actually do this all in our calculator at once. Start typing in your normal CDF. Start typing in your normal CDF, so second distribution, normal CDF. I'm going to put in 1.34, comma 10, 0, 1. I'm going to hit paste. For some of you, you've already gotten to this point. And then before I hit enter, I'm just going to write times 2 right at the end of all of that. Okay? If you have to do this in 2 steps, do it in 2 steps. Do the normal CDF first and then hit times 2. But our answer should be 0.18. And that's our p-val. Once we get our p-value, we move on to the the technical conclusion. So we're going to ask ourselves, is this p-val less than or equal to alpha? Is 0.18 less than or equal to the alpha we said at the beginning of the problem of 0.05? The answer is again no. No. So we fail to reject the null hypothesis again. Just like in the first example we did. We fail to reject the null. So now we're going to write out the script again. There is not enough evidence at the 0.05 significance level to show that, and remember now we put it into words. What's the alternative hypothesis? So it's not the claim. We don't talk about the claim here. We talk about the alternative. The alternative says the mean, which is the mean width of, or wrist breadth of women, the mean is not equal to 5. So there's not enough evidence to show that the mean wrist breadth of women is not 5 centimeters. So a lot of people get confused here because they think, well, the claim said it is 5, so they want to talk about 5, or they want to talk about the claim, because a lot of times the alternative hypothesis is just whatever the claim was. But for a not equals to problem, a lot of times this was not stated in the claim. So we don't word it the exact same as the claim, since this was not actually the claim. The claim was it was equal to, and we can't test equal to, so we tested it as not equal to, which is the only thing we can actually talk about in our conclusion. So there's a big problem, but this is one hypothesis testing problem. This is everything put together, and this is what your homework and tests are going to look like. Okay? And that's it for this lesson. Hopefully you understood it. If you didn't, reach out to me and I'll be happy